Hi friends, in this video we will discuss the basic definition of a basis of a vector space along with a few examples and two important theorems in the context of basis. The prerequisites of this lecture are span of a set and linear dependence and independence of vectors. What is a basis? A basis B for a vector space V is a subset of V that is linearly independent and B should span V. That is, V is equals to span of B. Let us look at some examples of bases of some vector spaces. First, if V is a trivial vector space, that is, B is equals to singleton 0, then B is equals to phi is a basis for V. Second, if V is equals to R, that is the set of reals over the field real, then B is equals to singleton 1 is a basis for V, since we know that a singleton set containing a non-zero vector is linearly independent, so B is linearly independent. Also, if we take any real number R, then R can be written as R into 1. That means R can be written as a scalar multiple of 1. So, this means that B spans R. Thus, B is a basis. Also, if we take B dash, which is singleton C, where C is any non-zero scalar, then B dash is also a basis for V. Since a singleton set containing a non-zero vector is linearly independent, so again B dash is linearly independent. Also, any R belonging to R can be written as R upon C into C. Now, R being a real, C being a real, this becomes a real number. So, R can be written as a scalar multiple of C. This means that B dash spans R. Hence, B dash is a basis. Next, let us take V is equals to R2. Let B is equals to 1, 0, 0, 1. Then it can easily be seen that B is linearly independent. Since if we take C1 into 1, 0 plus C2 into 0, 1 is equals to 0, 0, then we get C1, 0 and C2, 0. Thus, B is linearly independent. Also, if we take any AB belonging to R2, then AB can be written as A into 1, 0 plus B into 0, 1. Thus, these vectors span R2. Hence, B spans R2. Both of these conditions together says that B is a basis for R2. Now, let us take V is equals to R2 again, but instead of taking B is equals to 1, 0 and 0, 1, we take B dash as 1, 0, 1, 1. Again, it can be seen that B dash is linearly independent, since if we take C1, 1, 0 plus C2, 1, 1 equals to 0, 0, then we get C1 plus C2 is equals to 0 and C2 is equals to 0. Both of these conditions imply C1 0 and C2 0. Thus, B dash is linearly independent. Also, any AB in R2 can be written as A minus B 1 0 plus B 1 1. Thus, these vectors span R2. Hence, B dash spans R2. This implies B dash is a basis for R2. So we see that B and B dash both are a basis for R2. In fact, there exist many more bases like these. So from this, we conclude that a basis need not be unique for a vector space, but the number of elements in each of the bases must be same. We are now in a position to define dimension of a vector space. The number of elements in a basis determines the dimension of a vector space. That is, if B is a basis for V, then dimension of V is cardinality of B. Accordingly, we have finite dimensional vector spaces. So a vector space V is said to be a finite dimensional vector space if it has a finite basis. Secondly, we have infinite dimensional vector space. So V is said to be infinite dimensional if it has a basis which is not finite. So we have an infinite basis. So now that we know what a basis is and dimension is, let us take a look at some more examples to get a clearer picture. Now if we take V is equals to Rn, let us take B to be E1, E2, En, where Ei is a vector whose ith component is 1 and rest all are 0. So 0, 0, 0, 1, 0, 0. So this is my ith component. It can easily be seen that B is linearly independent and spans V. So B is a basis for Rn. In fact, such a basis is called a standard basis. Since B is a basis for V and there are n number of elements in B, so dimension of V is equals to n. Now if V is equals to M2R, so M2R is the set of all 2 cross 2 matrices whose entries are reals. So now if I take B to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Then again, it can be seen that B is linearly independent and spans M to R. So that means B is a basis for M to R. And because there are 4 elements in B and B is a basis for V, so dimension of V is equals to 4. Now if I have V is equals to P and R, So P and R is the set of all polynomials of degree less than equal to n whose coefficients are from reals. So if I take B to be 1, x, x square, xn, then any polynomial of degree less than equal to n can be written as c0 into 1 plus c1 into x plus c2 into x square plus cn x to the power of n. So that means that B spans V. Also, it can be seen that B is linearly independent. Hence, B is a basis for V. Also, dimension of V here is n plus 1 since there are n plus 1 elements in B. So all of these cases that we had taken till now were of finite dimensional vector spaces. Let us now take a look at V is equals to PR. So basically V is equals to PR, so that means V contains all polynomials. So there is no restriction on the degree of the polynomial. So now if I take B to be 1, x, x square and so on, then B would be a basis for V. Since B is infinite set, so that means V is infinite dimensional vector space. By now we know what a basis is, and now we are in a position to prove some theorems. So theorem 1. Let V be a vector space and B is equals to the set u1, u2, un. Then B is a basis for V if and only if each V belonging to V can be uniquely expressed as a linear combination of vectors of B. That is, each V belonging to V can be expressed in the form V is equals to C1U1 plus C2U2 plus CNUN for unique scalars C1, C2, Cn. Since we see here that it is an if and only if condition, so we have to prove both ways. So we will first assume that B is a basis for V, and we'll show that each V belonging to V can be uniquely expressed as a linear combination of vectors of B. Then for the converse, we'll assume that this condition is true and we'll show that B is a basis. So let's start the proof. So we first assume that B is a basis for V. So now we need to show that each V belonging to V can be uniquely expressed as C1U1 plus C2U2 plus CNUN. So we need to show this. Since B is a basis for V, that means that V is equals to span of B. So clearly, if I take V belonging to V, which is equals to span of B, that means that V belongs to span B. That means V can be written as C1U1 plus C2U2 plus CNUN for some scalars C1, C2, Cn. So the only thing that is left to show is that such a representation is unique. So we'll assume that the representation is not unique. So we are able to find some of the scalars d1, d2, dn such that V can be written as d1u1 plus d2u2 plus dn So using these two, we can write c1u1 plus c2u2 plus cnun is equal to d1u1 plus d2u2 plus dnun. This implies c1 minus d1 u1 plus c2 minus d2 u2 plus cn minus dn un is equals to 0. But since B is a basis, so u1, u2, un, that is B, is linearly independent. So this implies Ci minus Di is equals to 0 for every I going from 1 to n, which means Ci is equals to Di for every I is equals to 1 to n. That means that the representation phi is equals to C1U1 plus C2U2 plus CNUN is unique. Since it was an if and only if statement, so now we need to prove the converse of the same. So we'll now assume that every V belonging to V can be uniquely expressed as V is equals to C1U1 plus C2U2 plus CNUN, and we'll prove that B is a basis. Since according to the given condition, any V belonging to V can be written as C1U1 plus C2U2 plus CNUN, this clearly implies that B, which is equal to U1, U2, UN, spans V. So the only thing that is left to show is that B is linearly independent. Because for B to be a basis, we need B to be linearly independent and it must also span V. So let us now see. Let us take C1 U1 plus C2 U2 plus Cn Un is equals to 0. But according to the given condition, the representation of 0 as a linear combination of U1, U2, Un must be unique. But 0 can also be written as 0 into U1 plus 0 into U2 plus 0 into Un. And since the representation has to be unique, this implies that Ci is equals to 0 for every I going from 1 to n. Since Ci is equals to 0 for every I going from 1 to n, this means that B is linearly independent. Now B is linearly independent. B spans V. So these two statements together say that B is a basis for V, which is the required result. Let us now move on to the next theorem. If a vector space V is generated by a finite set S, then some subset of S is a basis for V. Hence, V has a finite basis. So it is given that there is a vector space V which is generated by a finite set S. So that means V is span S. We need to show that there exists some subset of S that is a basis for V. So let us see. There are two cases. The first case, S is either empty or it is equal to singleton 0. Now, if S is empty or singleton 0, in this case, this implies V is singleton 0. And in this case, phi is the required basis for V. So now, if V is singleton 0, then phi is the required subset of S that is a basis for V. So let us now assume that S is neither empty nor it is singleton 0. So there exists a non-zero element. I've taken U1 that belongs to S. So U1 is not equal to 0. Now clearly singleton U1, if I take, this is linearly independent. So let us now choose another element U2 if possible, such that U2 is an element in S, but U2 does not belong to span of singleton U1. If possible, we will choose this. If not possible, if there does not exist any U2 in S that does not belong to span of U1, so in that case it means that U1, span of U1 is equals to span of S, which in turn is V. So in that case singleton U1 would be our required basis. So let us assume such a U2 exists. So after this step, we'll get a set U1, U2, which would be linearly independent because U2 does not belong to span of U1. Now again, since U1, U2 is linearly independent, we aim at finding another element U3 which belongs to S, but U3 does not belong to span of U1, U2. If such an element does not exist, then that means this is our required basis. So we are assuming that U3 exists. So we continue this process until we get T, which is equal to U1, U2, Un, to be the largest subset of S which is linearly independent. So it is the largest linearly independent subset of S. So now I claim that T is a basis for V. Since it is given that S spans V, to show that T is a basis for V, we only need to show that T spans V, because we have already assumed T to be linearly independent. So if T spans V, then T becomes a basis for V. Since V is generated by set S, so if we show that S is contained in span of T, then we are done. So let us see. We'll take a general element in S. Now there are two cases. Because T is a subset of S, this S would either belong to T or S would not belong to T. So these are the only two cases that are possible. So if S belongs to T, then S would definitely belong to span of T. And then we are done. So let us now take a look when S does not belong to T. Now when S does not belong to T, then T union singleton S, when I take, this becomes my linearly dependent set, because I've assumed that T is the largest linearly independent subset of S. So this being a subset of S will be linearly dependent. Now because T union singleton S is linearly dependent, so that means that S belongs to span of T. So that means in either cases we are getting S belongs to span of T. So that means our subset S is contained in span of T. Hence T spans V. T spans V. T is linearly independent. So that means that T is a basis for V. Hence, V contains a subset of S that forms a basis for V. So we see that according to this theorem, whenever we have a subset that spans the vector space, then that subset will always have another subset which will be a basis for V. That means that if S is any set that spans V, then a subset of S will be a basis for V. Based upon this theorem, let us take up an example. Now here in this example, we have taken V to be R3 and I have taken S to be 2, minus 3, 5, 8, minus 12, 20, 1, 0, minus 2, 0, 2, 1, 7, 2, 0. So there are 5 vectors U1, U2, U3, U4 and U5. We first need to show that S generates V. And now when S will generate V, we need to find a subset of S that will form a basis for V. So for the very first step, we need to show that S generates V. So we need to take a general element of V. So a general element of R3 would be A, B, C. I need to show that this element can be written as a linear combination of U1, U2, U3, U4, U5. So let us assume that there exists scalars C1, C2, C3, C4, C5 such that ABC can be written as C1U1 plus C2U2 plus C3U3 plus C4U4 plus C5U5. Now this set S would generate V if this system is consistent for every value of A, B and C. So from here we'll write down the augmented matrix of this system, which will come out to be 2, minus 3, 5, 8, minus 12, 20, 1, 0, minus 2, 0, 2, 1, 7, 2, 0, A, B, C. After writing down the augmented matrix, we'll find the RREF of this matrix. Now the RREF here, I am writing down directly. So RREF here would come out to be 1, 0, 0, 4, 0, 0, 0, 1, 0, minus 2 by 3, 4 by 3, 1, minus 2 by 3, 25 by 3, 20 by 7, and then we have here minus B by 3, 2B by 3 plus A, 3A plus 3B plus C by 7. This is not RREF, this is the echelon form, and from this echelon form it was clear that this system is consistent for all the values of A, B and C. Now since the system is consistent for all the values of A, B and C, so that means that S generates V. Now further, we were supposed to find a subset of S that forms a basis for V. Now that can be done directly from this augmented matrix. So if we take a look at this augmented matrix, we see that the pivots are in the first, third and fourth column. So this is the first, third and fourth column. So accordingly, this means that the vectors U1, U3 and U4 are linearly independent. So this means that the required subset of S that will form a basis would be T, which is equal to U1, U3, U4. That means T, which is equal to 2 minus 3, 5, 1, 0, minus 2, 0, 2, 1. So this is my required subset of S, that is a basis for R3. I hope this example and this entire video is helpful to you all, and if there is any problem that is encountered during this entire session, then please feel free to comment below. Thank you very much.